Hello, T-Rex math students. Today we are going to work through investigation 4, mainly problem 4.2, where we're finding the slope of a line. So what is slope, you might ask? Slope is actually something we've seen before. Slope has a special formula. It is rise to run, and it's talking about the steepness of a line. When we think about slope, we want to think of it in terms of the vertical axis compared to the horizontal axis. So the x-axis is on the bottom of the comparison and the y-axis is on the top of the comparison. Believe it or not, we have seen this before. When you think back to Henri and Emile's graph, the steepness of Emile's line, that steepness that you see, is because of the slope. Henri's line is not as steep, and his slope is not as great as Emile's. In these cases, Emile's slope was 2.5, whereas Henri's slope was 1. The slope can always be found as the coefficient right in front of the independent variable. In Emile's case, it's 2.5 for every 1 second, and in Henri's case, it's 1 meter for every second. In this line that we've previously graphed, you can see that this line goes downward. That would mean that this line has a negative slope. And in this case, it started at 100, and for every 10 down, it ran 1 to the right. So the slope would be a negative 10 to 1, because its rise is down by 10, its run is over to the right 1. And finally, in the case of Alana, Gilberto, and Leanne, you can see that their slopes are very different. Leanne, who was this line, had actually 0 slope because her line didn't increase or decrease. Alana's line had a slope that was not as steep as Gilberto's line. Gilberto had a much greater slope than Alana because you can see the steepness in the comparison. So let's look at that formula again. In your notebooks, let's go ahead and write slope equals rise over run, or vertical change over horizontal change. So in this actual graph that you see pictured here, some of us have seen this graph before, there are 2 points on the line, and to get from one point to the other, you go up 2 units or rise 2 units on the y dimension and go to the right 3 units on the x dimension. So the slope is 2 to 3 or 2/3. In this picture, you can see that the line goes downward. So it's going to have a negative slope. In this case, again, there are 2 points on the line, and instead of going up, we go down 2 units, or our rise is -2, and our run is +3. As slope, it would be written as -2/3. This graph, again, has a negative slope because you'll notice the line is going downward. If I pick 2 points, like these two, and I go down 6, that would be a vertical change of -6 and a run of +2 because I'm going to the right. So my slope simplified would be a -3 for every 1, or -3. And in graph 2, if I choose 2 points on the line, again, this one you'll notice the rise is up 6 units, and the run is over 2 units, And simplified, it would be a positive slope of 3 to 1 or 3. We can investigate the same pattern in slope by looking at a rate table. In this rate table, you'll notice that the y is our vertical distance because the y-axis is vertical, and our x coordinates would represent the horizontal change. So if I look at the patterns in this rate table, I'll notice that my vertical change is +3 every time, whereas my horizontal change is +2 every time. So my slope is 3 to 2 in this rate table. Again, I can do the same thing with table 2. If I look at my y-axis, every time I am going down by 0.5 every single time. So my vertical change is a negative 0.5, whereas my x-axis goes up by 1 every time. So my horizontal change is 1. My slope then is negative 1/2 over 1, or just negative 0.5. Last but not least, we can look at an equation, and we know from before that the rate of change is the number that goes right in front of the independent variable. We've been calling that a constant rate of change and also a coefficient because it goes with the variable. This number that's in front of x is also called the slope. So the slope would be 2.5 in equation 1. The y-intercept would be this number right here that gets added on. That is where our line starts or crosses the y-axis. In the case of this second equation, the number that's right in front of the variable, that coefficient, is -3. That's our rate of change. So we can also consider that -3 as a slope. That would mean our line would go downward. Okay? This number that's right here without the variable would be considered our y-intercept because that is where it would start or cross the y-axis. So what can we take away from all of this? We want to start to notice that every time we have an equation, a graph, or a rate table, it's going to follow a specific formula. You can think of an equation as 3 parts. You've got your number in front of your independent variable, and that is considered your slope, or m. And then the number that's added on or subtracted is considered your y-intercept. This equation that we've written here is called slope-intercept form in algebra, and it's a formula we can use. Some people like to write their equation as y equals and start with their y-intercept and then add or subtract their slope multiplied by your independent variable. So if you choose to write it this way, B still is going to represent your y-intercept where the line crosses the y-axis, and the m stands for the slope or the rate of change in the equation. Let's take one last look at this poster from our classroom and see if we can take Emile's equation and piece it together with the formula y equals mx plus b. So if I look at Emile's equation, his equation has d equals 2.5t. Not the same variables, but the number that comes right before the independent variable t, that is our slope. And because there is nothing added on in this equation, we could think of it as +0. So that would mean the y-intercept is 0. If you look at Emile's graph, look at the y-intercept is 0, and the slope is 2.5 for every one. Same thing with Henri. Henri had a slope of 1, or d equals 1t plus 45. Notice his line is not as sloped, but the y-intercept is 45, and that's where the line starts.